All right, recording is rolling. Welcome to Tuesday, September 19. I have a friction lab lined up for you guys. You guys got this page on your desk? This page? Okay. Now, there's two halves to this friction lab. The way we're going to do this is I'll walk you guys through the first half. Well, here, I'll have you guys do the first half. Then about halfway through class, I'll restart the video and then we'll help you guys out with the second half. Okay. Now, on the back side of this paper is Outward Lab. So hold on to this paper at the end of class, just because we're gonna do a different lab, probably tomorrow. I'm thinking. I think tomorrow we'll do that one. Okay. Before we get rolling on that, here's top scientists for projectile motion. Top scientists for projectile motion. So awesome job if you are on that list. Let me tell you, after teaching physics so many years, a lot of students find projectile motion to be like one of the hardest things that we do in physics. So yeah, so definitely awesome job there. Now, I haven't handed these quizzes back yet because I'm still waiting for a few more to come in. Right, a few late entries, but in time. All right. Okay, and then yesterday we did some textbook puzzles. Those aren't due until 29th. So you guys want?
Yeah. What about the linear motions?
Linear motion quizzes? Yeah, those are bad. Yeah. So you guys see those folders hanging in the back there? Right. Now you guys have the yellow name tags. You guys have the yellow name tags. Yeah. So your linear motion quizzes is bad. Yeah, you can do corrections. Yeah. So if you find the ones you missed, just handwrite out the solutions to the turn back the grade grade, then give partial credit back. Yeah. All right. So this lab it's in two halves. The first half actually got a free body diagram for the first half right here. Right. There's the question you guys are going to try to find is what is the coefficient of friction, coefficient of kinetic friction between two surfaces, right? Here. So the mechanics are you got spring scales, you guys got different lab weights. You can pick the spring scales up. The brown ones are good for like maybe the medium large lab weights. Now, if you're dealing with small forces, maybe the blue spring scales are a little bit better. Right, so you guys got one of each. Okay? What's the force to lift it versus what's the force to drag it? Now, the lifting force could tell you what the weight is, right? And if it's in fact if the weight's just sitting at rest on a flat horizontal surface, then the weight would be balanced out by the normal force, which again you could get just by lifting it with the spring scale, however much weight that is, right? In newtons, wouldn't you be measuring this in newtons? Guys, on the spring scales today, are you guys measuring grams or newtons? Newtons, because that's a force to measure a force, how to quantify a force, right? Okay. Then if you drag it across at constant velocity with the spring scale like this, okay? And guys, constant velocity, is that an example of equilibrium? Equilibrium? Yeah, it is. So zero acceleration, zero net force. Right? Equilibrium might mean at rest, or equilibrium might mean constant velocity. Right? So we're going to do the constant velocity version today because that gets at a type of friction called kinetic friction. Right? And there's some coefficient of friction. There's some ratio here. Oh, do you guys see what coefficient of kinetic friction? That's what this is defined as. It's the ratio of these two right here. What's the friction force compared to the normal force? Is that right? And as long as you pull at constant velocity, then whatever the spring scale rating is, again, as long as you're pulling horizontally, right? Whatever that spring scale rating is telling you what the friction force is. They have to be the same value because they're balanced out so that you get constant velocity. Right? One is the other. Okay? Right. So the ratio of these two will tell you coefficient of friction. Okay. Now, coefficient of kinetic friction is a material concept. Right? So once you know what materials you're working with, like if I've got steel versus aluminum, right? Like that is a known quantity, what the ratio of these two is. Oh, look, it's like the same diagram, just small up there, right? Right. So what's this friction force compared to that normal force? Now, if you look down the list here, do you guys see coefficient of kinetic friction as, I don't know, maybe about 0.3? Sometimes it's a lot less, sometimes it's a lot more. So kind of a middle ballpark number is about like 0.3-ish, somewhere there, right? If you have coefficient of kinetic friction of like 0.3, what that means is that this friction force is 30% of this normal force. Right? So you can swap out different weights and it'll get like different friction forces, like if you're pulling at a constant velocity. Right? But the ratio of those two should be sort of predeterminable based on the materials you're working with. So I have this bare metal against this paper, right? That could be like some value. And that's what you guys are trying to figure out what it is. Right? You guys got that? Good so far? Right. Now, side note here, I'm going to take you guys one layer deeper. this is like a practical application of the. So you guys are doing the fundamentals today in this lab, but I want to show you guys if you apply this a little bit more complex, what you can get from that. You get car braking to a stop, right? Now, car braking to a stop is not equilibrium, right? So there's net force on it. The net force would be the friction force, right? And the rate that it can slow to a stop, you think it has something to do with the coefficient of friction between the tires and the road? The tires and the road? Actually, that's exactly what shows up on this table. I've got 3 different kinds of roads. I have an icy road, a wet road, and a dry road. Ooh, do you guys see different coefficients of friction for those different situations? Right? Did I tell you guys about anti-lock braking? Anti-lock braking? We talked about that? Right. Okay. So when you guys got your driver's license, you had to learn about anti-lock braking, right? So anti-lock braking, the idea is that when you slam on the brake, right, you try to stop in a hurry, the wheels don't actually lock, right? Hence anti-lock, right? The wheels actually rotate forward a little bit. There's a whole computer system that navigates that, right? Why would you want that? Because if the wheels lock and this car goes, starts skidding across the surface, that's kinetic friction you're taking advantage of. Versus if the wheels can rotate forward a little bit, you can actually maintain static friction with the road, which is actually, you're going to get more friction. You guys see over and over, this red number is larger than the green number all the way down. Static friction, you always get more than kinetic friction. Therefore, the car can stop sooner than if the wheels are locked. Right? Now, if you go back many decades ago, they used to tell you to pump the brakes so that you could try to sort of achieve that effect. But the new advice is don't do it. Go ahead and slam the brake, and the computer system will take over, so it can try to knock you over into static rather than kinetic friction. Right? But today, we're just more simply going to focus on this kinetic friction. So here's icy road, wet road, dry road. Right? Ooh, so like 5%, 40%, 70% that you're comparing. What is this friction force compared to that normal force? That has something to do with the rate that the car can slow down. Oh, look at this proof here. Here's Newton's second law of motion. The net force is the friction force in this case. Friction force is coefficient of friction times the normal force. So maybe like 40% of the normal force if it's a wet road, for example. Right? And then the normal force is equivalent to the weight as long as it's horizontal road, nothing crazy going on. So the substitution right there in brackets. Guys, what cancels out in this proof? What cancels out both sides? The mass of the car? You guys see the mass of the car cancels out? Hey, what does that mean? Does that mean, suppose you're driving a car just by yourself, okay, at some speed, some road, blah, blah, and you slam the brakes, come to a stop in some distance. Now let's go back and rerun that, except let's have all your friends are in your car, you guys got the trunk is loaded up with groceries, right? It's a huge, heavy car. And otherwise everything's the same, the initial speed, the road, blah, 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 right? Brake to a stop. What is that braking distance with a really heavy car compared to a really light car? What's the braking distance? The same. Yeah, you see what happens the same? Because the mass of the car cancels out. So it slows down at the same rate. That's what acceleration is in this case. Right? Acceleration is the same. Therefore, everything else, all the kinematic motion is the same. It breaks side by side, same distance. Right. Oh, here's coefficient of friction times the gravity field. Okay, so it might be like 0.4 if it's a wet road, right? 40% of the gravity field can tell you the rate that the car can slow down. Okay. All right. So that's a little bit more complicated application of what you guys are doing today. Okay? Then we're going to get to the second half of the lab and save that for like halfway through class. So let's just focus on this part first. Okay. You guys have a lab table. It says very simply, find what are the weights in newtons. You just very simply lift it with the spring scale. What's the dragging force if you drag across the paper at constant velocity? Right. Take the ratio of those two, have you guys make a graph. About halfway through class, I'm going to restart the video and show you guys how to put this together. In the meantime, I'm going to be walking around and checking on you guys. All right, so let's stop the video right there.